Alright, hell yeah. So we have the most difficult physics problem, projectile motion. This is physics for scientists and engineers. Booyah, let's get into it. Now this is a quick solution. This is the solution I'm going to go over. But this has one just major hiccup of like, hey, like how do you solve it? And so that's what we're going to go over. Anyway, so you have a soccer person kicking a ball on top of a hemispherical rock. And if the person just kicks the ball at a slow speed, it might just dribble down the rock. If he kicks it straight with enough speed, it might actually come back and hit the rock. So we need to know what the velocity is that it's not going to, you know what I mean? It's going to clear and it's never going to touch the rock. Hell yeah. And then once we find that, we need to know the distance it hits out. Alright, let's dive in. So the technical solution is like, hey, this is the equation of a circle. And so I'm going to put my datum here. This is the x direction, this is the y direction, this is 0. If x is 0, booyah, I'm going to have a height of r. So this is going to be the equation of this circle. Kinematics says that if I kick this with an initial velocity, nothing's slowing it down. There's no force on it, no air resistance. There's no big earth over here sucking it towards it. But there is an earth here that's going to suck it down. But velocity and acceleration, and position, they are vectors. And so you can treat them, you know what I mean? We're going to treat them in the x direction and y direction separately. And that's what we do for kinematics. So and I'm just going to show you kind of the solutions. So these are the kinematic equations. I derived them from integration. I'm not going to show that. But now we know at any given time, I know the position, because if I impart an initial velocity, hell yeah, it's just going to be going that way at a constant speed. In the y direction, it's going to be picking up speed at a rate of 10. It's going to be increasing in velocity at a rate of 10 meters per second per second. Booyah, that's gravity. So that's what we did. We used a factor. We said gravity is 10, so this is the equation. After you integrate, you get this. Your position in the y is going to be, well, we're going to start at r, and then we're going to rapidly reduce that until we hit the ground. Cool. All right, and then so these are our kinematic equations. They're functions of time. At no point are either of these equations a visual representation of what's going on a side view. To do that, we would need this projectile equation to be the soccer ball y is a function of x. Just like the circle is y is a function of x. I can see that from a side view. So to do that, I can recognize that at any given time, let's say 1 second, both of these are 1 second, that's going to be the coordinates, the x, y coordinate of the soccer ball at any time. So as long as these times are the same, that's going to be the coordinates of the soccer ball. And so that's what we're going to do. We're going to solve one of these for t. Obviously easier to solve this for t. And we're going to shove this quantity into there. Once we do that, I'm going to get an equation. Y is equal to, so this is going to be x squared, v squared. We have that negative 5 plus r. Hell yeah, how are we doing on time? We're doing pretty good. Okay, so this is the function of the actual projectile. You know, I gave it that little symbol. This is a half circle, quarter circle, and so that's the equation for the hemisphere. So now, and this should be squared. So now I had to Google this. You know, after I've made a couple solutions, this was the best one. Be like, hey, what is the mathematical way to know when one function is always larger than the other function? So let's come back to this, because what we want is the projectile function to always be larger. I want a way, because I don't know, maybe it's larger at the start, but then comes crashing down into it. You know what I mean? You know, maybe it's larger at the start and then clips it right there and then passes it. How am I supposed to know that? And so what we need to figure out is that one function is always larger than the other over, you know, over an interval is what that would say. And so to determine that, they say, well, you're going to take the difference of the two. If one function's up here and the other function is here, here's the difference. And I need that difference to always be, you know, a number greater than 0. So they're going to do that greater. So I'm going to take the If this is the function and this is the function, if I subtract this one from that, I'm going to get that space. And that always has to be a number. Now to make this easier visually, I'm going to, because this is a square root, I'm going to square both sides. So we can't bite off more than we can chew. So I'm going to square both sides, but we do need to crush this out. So I squared that side easy. Squaring this side is a little bit harder. So, you know what I mean, this is for the pros. But you're going to square this term, 25x to the fourth, vi, that's velocity initial to the fourth. You're going to square this term. Cool. And then you're going to have that second little term, it's these two together. And then you're going to have to multiply it by 2. That's kind of the foily part. So, booyah. So I have negative 10x r x squared vi squared. We got to crush. But anyway, so now I have, and I just set these equal. You know what I mean? Because I have no idea how to use those. My mind's just going to blow. But anyway, if we set them to equal, then we're going to say, hey, the difference is nothing. And what that's going to, because we have a third variable, or just another variable. It's this vi. I don't know what this is. And so I'm going to set these two equal. And then I'm going to, hey, these r squareds can cancel. And then let's get this over to the other side. So then now I have an equation that's equal to 0. All I did was just get this to the other side. And now but I need to solve for vi. How are we doing on time? All right. So I'm going to multiply everything by vi to the fourth. And so what we do here is now this becomes x squared vi to the fourth. This becomes this, you know what I mean, that term, vi to the vi squared, because we only have 2 up top. This will just be 25x to the fourth. Okay, now we don't want to worry about our x terms yet. We're just going to treat those like constants. So we have something that looks like ax squared plus bx plus c. I need to divide by my a term, so I'm going to solve this by hand. And how I do it is, you know what I mean, divide everything by the a term. So that goes away, and this becomes x squared. Get this term to the other side, so we have negative 25x squared. Okay, and then that's not there yet. And then so we've reduced this. We divided by the x squared everywhere. And then we treat this, even though this is to the fourth, and we just treat this like it's just x squared and this is x. That's how you treat that. And then so we say, you know what I mean, vi squared minus, we're going to have half of that. Cool. And then when we square it, we're going to pick up the extra term, which is this 100 r squared divided by 4. And hell yeah. And now I can, and that's going to be this, you know what I mean? And now I can take the square root of both sides, plus or minus, and then I can add this to the other side. How we doing? All right, 2 minutes. And then we have our solution. So, I mean, this is vi squared. Instead of solving for x squared, you're solving for vi squared. Cool, you know what I mean? You're treating this like it is x squared, and you're treating this like it is x. So when you solve for x, you get vi squared. You know what I mean? So to get the actual answer, you need to take the square root of all this. But we'll get to that in a second. Okay, hell yeah. So now what we need to know, the easiest thing to do is just throw x is equal to 0. And just all we're trying to do is figure out the value of our velocity. How big can we make it for that difference to be 0? We throw in 0 here. This becomes 10r. Once we take the square root, 10r divided by 2, plus or minus 10r divided by 2, plus 10r divided by 2. We want the biggest quantity, so we're going to use the positive root, and we're going to get 10r. And that's going to be v squared again. So v is square root 10r. We got 1 minute. We can crush this out. And then because this is negative, for any value x that's greater than 0, you know what I mean? That means that the velocity, it's going to reduce this over here. And then so my velocity at x equals 0 has to be this. At the other, my velocity could be smaller. You know what I mean? So it's that difference means it's always going to be overshot. I think I'm explaining that. And then, do we even have time to do this? 19. Well, let's do this in 2 parts. Alright, I'm glad I took a breather, and we're going to just go over 10 minutes. Because this is the most important part. You know, if I solve it for x is equal to 0, I get the largest number. The value for the velocity is going to be the square root 10 divided square root 10r. And if I throw in any value of x, I mean, I could throw in a value of x in between, x for sure has to be between 0 to r. So I could throw in r and see what I get. And if I do that, this is a negative term, so it's going to reduce this. And then I don't want to have the negative root. That would reduce it even. I'm going to still take the positive root, but this number is going to be smaller. So I'm going to have 5r over here, and then plus a smaller number than 10r, than 5r. You know what I mean? So just keep that in mind. And then my velocity would be smaller than this. So that means as my x gets out here, I can have a larger value of velocity. So, and that's kind of interesting. Even though this velocity does not change, you could set up a parameter where if this velocity, if you had a lot of wind and you had a constant change, then I could slow this velocity down and it still wouldn't hit. That would be actually a more advanced problem. And I think that shows it. It shows that if I choose any value of x that's greater than 0, and I can choose r, and that's the last place the rock is. And as I progress, this negative is going to reduce that. So I can have a lower velocity and still not hit the rock. And we chose to get rid of the less than or greater than sign. We just chose them equal. So in any case, the velocity has to be just bigger than that to miss the rock. But as we move in this x direction, this velocity don't need to be the biggest. Right at the start, hell yeah, it has a real tendency to just run into the rock right away. And so that's where it needs to be this biggest value, and it is. So now to solve the problem, so that's problem A. That's the minimum initial speed. It's square root 10 r. And then with this, how far from the base of the rock does the ball hit the ground? So we're going to go back to our kinematic equations. It's going to hit the ground when y is 0. So I need to find the time when y is 0. So I'm going to throw in 0 to this equation. We're going to get negative r over here. Negatives go away. I'm going to divide r by 5. R divided by 5 and the square root. So we get that time is going to be the square root r divided by 5. And I'm going to take that time and put it into the x equation. That's going to be the velocity we found. We're going to give it a square root 10 r. So we have this equation. X is equal to velocity initial times time. This is our velocity initial, and this is the time that it's going to hit the ground. So this is the position it's going to hit the ground. And we can put everything, have a square root, and we're going to have 10 divided by 5 is 2. This is going to be r squared. Square root everything, we're going to get square root 2r. So that's the position from here. Now I chose the datum to be here, so that's square root 2 times the radius. Hell yeah. But they want to know from here, this distance. So, you know what I mean. My x does not line up with this x. My x is from this datum here. So I'm going to say their x is x prime, or x star. So I'm going to say they're trying to find x star, which is my x divided by r. So that's all I have is square root 2r minus r. And I'm really satisfied with this one because I did a 3-hour video. That's going to be posted tomorrow. I actually found a solution that was jivey, just looking at this equation and being like close enough, and I'm pretty confident. And then it was very useful to be like, hey, what is the mathematical way? Using AI just a little bit to be like, hey, like what is the solutions? What's the ways to solve something like this? And then we do it in a very technical way. So hell yeah. So we're about 15 minutes, and I'm pretty satisfied with this one. And so that's the distance. We're going to have this minus r. I'm going to factor out the r, and I'm going to get r square root 2 minus 1. Now, I did plot this, and in the 3-hour video, we chose a radius of 5 meters, and then we just kind of guessed, and we honed in using kind of the guess and check method that the velocity was close to 7. And so at a radius of 5 meters, the velocity is going to be square root 50, which is 7.07. 7.07. So square root 2 times, what do you call that? Square root 2 times 10? Is that what it is? it was the square root 2 times 10 divided by 2. Is the square root 2 divided by 2 times 10. Square root 50. But anyway, so that's what I graphed on here. Hell yeah. The red is the hemisphere, so we're going to end with that. The red is the hemisphere of the rock, and then the blue is the projectile. But this is just a conundrum because you just never know if it's going to clip somewhere else mathematically. And so, and you're using a different, you know what I mean? I thought this was very unique because it's not differentiating, it's not integrating. It's actually figuring that the difference between functions, and we squared them because the difference between the square of if here's the functions and then we square them, they're going to get farther apart, but still as that difference approaches 0, when we actually get velocity in there, that's what we did. We set them equal to 0, so it don't matter if we squared them, and that just made the math a lot easier. Alright, so hell yeah, so I'm pretty satisfied with this. A very difficult problem. Physics for scientists and engineers. This would be your freshman level physics, and I almost failed my sophomore year. Actually, I almost failed both years. Physics was hell, just because there's so many different unique problems, and no one has a basis of like, hey, how do you actually get a foundation for this stuff? So tomorrow I'm going to post that 3-hour footage, and it's actually, I would watch it. I'm not going to watch it, but it could be worth watching, you know what I mean, in the future. Alright, so hell yeah. You know what I mean? When there's nothing, when you can't breathe the air outside, that's what my videos are for. The future. Alright, thanks for joining me, and that's a video.